The breakthrough came from the Perseverance rover, exploring Jezero crater since February 2021. Over 4 years, it collected more than 40 rock and soil samples. In 2025, the first batch finally arrived on Earth through the Mars Sample Return mission, traveling over 480 million kilometers. Under the microscope, scientists found microscopic structures in the rocks, patterns too complex to form without life. These tiny microbial fossils contained organic molecules, carbon compounds, and even traces of ancient water. Simple life, yes, but it's life nonetheless. Experts worldwide reacted cautiously, but the excitement was palpable. This changes everything we thought we knew about the solar system, said one astrobiologist. For humanity, it's a reminder. Life is not unique to Earth. While Mars grabbed headlines, another discovery quietly reshaped our view of distant worlds. The Vera C. Rubin Observatory surveyed over 500 million stars in 2025, identifying dozens of new exoplanets. One, located 320 light-years away, showed atmospheric signs of water vapor, methane, and possible oxygen-like molecules. Scientists stress this is not proof of life, but it is an exciting clue. The building blocks for life are likely common. Imagine Earth-like chemistry occurring elsewhere in the galaxy. The more we look, the more we find worlds that mirror our own. Mars and exoplanets aren't the only frontiers. In 2025, the Lunar Echo mission landed on the far side of the Moon, using ground-penetrating radar to discover massive underground voids, cavities formed by ancient volcanic activity. Some are over 100 meters wide. Scientists suggest these voids could become the first human habitats on the Moon, offering protection from radiation, meteorites, and temperature extremes. Elsewhere in the solar system, missions observed asteroids with incredible precision. NASA's DART mission tracked asteroid deflection techniques, while the James Webb Space Telescope imaged distant gas giants with unprecedented detail. Saturn's rings, composed of billions of ice particles, were analyzed for their age and movement patterns. Even Jupiter's smallest moons revealed volcanic or icy activity. These discoveries were made possible by advanced robotics, AI, and next-generation telescopes. Without them, we would still be looking at stars as distant, lifeless dots. Every new finding inspires students, researchers, and dreamers. It reminds us that curiosity drives progress. Each mission, each sample, each exoplanet teaches us about ourselves as much as it teaches us about the universe. Jupiter's Great Red Spot has been raging for at least 400 years, and possibly much longer. Recent observations reveal that the storm is slowly shrinking in width, yet its winds remain extraordinarily powerful, reaching speeds of over 600 kilometers per hour. The swirling cloud patterns change color from deep crimson to pale orange, likely due to chemical reactions in the upper atmosphere. Jupiter's lightning is the strongest in the solar system. Individual bolts carry millions of volts, far exceeding terrestrial lightning. These storms occur deep in the atmosphere, where high pressure and fast-moving convection currents produce enormous electrical charges, creating thousands of lightning strikes per day. The planet emits more energy than it receives from the sun. This excess heat is generated by the slow gravitational compression of hydrogen, a process known as Kelvin-Helmholtz heating. It is enough to make the planet glow faintly in the infrared spectrum, revealing atmospheric storms invisible in visible light. Jupiter has at least 95 confirmed moons. Io is the most volcanically active body in the solar system, with hundreds of volcanoes constantly erupting. Lava fountains can reach heights of up to 500 kilometers. The heat powering these volcanoes comes from tidal forces caused by Jupiter's immense gravity pulling and flexing Io's crust. Ganymede, the largest moon in the solar system, has its own magnetic field, the only moon known to have one. Its magnetic field interacts with Jupiter's magnetosphere, creating auroras at the moon's poles. Callisto, heavily cratered, has a surface that has remained mostly unchanged for billions of years, preserving a record of ancient impacts. Jupiter's magnetosphere is the largest structure in the solar system, stretching up to 7 million kilometers toward the Sun and almost reaching Saturn's orbit on the opposite side. Trapped charged particles form radiation belts thousands of times stronger than Earth's Van Allen belts, creating lethal conditions for spacecraft without heavy shielding. Jupiter's auroras are among the most powerful in the solar system. Energetic particles spiral along magnetic field lines and collide with atmospheric gases, producing light thousands of times more intense than Earth's northern lights. These auroras are constant, visible even from spacecraft orbiting the planet, and reveal interactions between the magnetic field and charged particles. Jupiter's internal structure is unlike any planet in the solar system. Deep inside, hydrogen exists in a metallic state due to immense pressure, conducting electricity and generating part of the planet's magnetic field. Scientists estimate that the metallic hydrogen layer extends thousands of kilometers below the visible cloud tops. High-altitude winds on Jupiter reach extraordinary speeds, with some jet streams moving faster than 600 kilometers per hour. These winds create complex wave patterns, turbulence, and vortices that interact with storms like the Great Red Spot, continuously shaping the planet's ever-changing atmosphere. The Juno spacecraft has mapped Jupiter's gravity field with unprecedented accuracy, revealing small irregularities that suggest massive flows of liquid metallic hydrogen deep inside. These flows influence the planet's surface weather and magnetic field, connecting the hidden interior to the storms and radiation belts observed above. Subscribe to the channel to get notifications about new videos. See you in the next one.